Yes. Okay. Can you see my screen now? Just let me know. Sure. Yeah. I guess this works. Okay. Let's get started. Shear force effect. Okay, this is a case. So we are gonna check and examine today where there is only shear force on the section. Okay, there is only shear force on the section. So let me write here. There is only shear force on the section. Here, I should remind you what we learned while we are drawing the internal force diagrams. The shear force T equals dm over dx. Okay, this means if we have a shear force on the section, there is always a moment. Bending moment. Moment on the section. So what we said at the beginning, we said we're gonna work on only shear force on the section, but according to this mathematical equation, it says if there is a shear force, there is one moment on the section, bending moment. But here, the bending moment is less, very small value. So we ignore the moment is ignored in this behavior. Okay, since moment is so small, when we compare with shear force effect, we ignore it and we take into account only shear force in our case. So let's have some examples. For example, where if we have a small or short cantilever, for example, let me draw here. This is the wall. Okay, we insert this, let's change the color. We insert this portion, a small block. So if we apply a force here, there is an eccentricity. That means there will be a moment around this region. But when we compare it with the shear force effect, it's so small. That's why we ignore that. So we take into account only shear force effect. So if we cut from this section, what we will see? We will see a rectangular section. On this section, we have shear stress. Shear stress, remember, is a kind of stress, but the stress mean is the force over area, but here the force is parallel to the surface. Okay, parallel to the surface, parallel to the plane, but the calculation is same, force over area. That's it. Here we have, this is tau, and we have here an area. If we say here V, the force is V, the tau equals V over A. The logic is same. This is force. This is area. It's almost same like the axial force. Remember, if we have a surface and which is, if there's a force perpendicular to this area, we have axial stress like this, and we call it like sigma. So P over A. But here the case is same. The force is in this direction, parallel to the area. Parallel to the area. So we have stresses in this direction, which is again parallel to the area. Tau is here. Again, if we say V here, V over A. So again, this is force, and here is force. Okay, force over area, force over area. Another example regarding this behavior. Sometimes we connect two timber members to each other with glue. Okay, let me draw it. For example, here we have a timber member, timber plate, and there's also one here. We apply a force. So what we do, we transfer this force from this member to this member. How? Here there's glue. Okay, this portion transfer this loading to other piece. Okay, let's have a look this section here. If we take a look here in plan, and here in this portion we have glue. So this force is parallel to this area, right? Parallel to this area. That's why there will be a shear stress again on this glue area. We are going to calculate the shear stress first, and then we will check it with the allowable shear stress of the glue. If our calculated stress is less than the allowable stress, yes, this glue works and transfer all loads to other member. Otherwise, if the calculated one is greater than the allowable, no, that means there is a problem. Change the member. That means we need a big area. So we increase the sections. Here, this is V again. This is tau, and the surface area is A. So it's V over A again. So at the end of the day, we know what the shear effect is on the section. We, as I said, we ignore the bending effect on the section. If there is shear on a section, I'd like to say a few things about the deformation under shear loading. If we have a rectangular member, so if we apply shear stress to this member, it's gonna get this shape. Under this stress, it will, all these stresses are same. It's gonna get, by the way, let me draw the rectangle again. Makes an angle over here. This is the shear deformation. Under the shear loading, the structural members tries to do this deformation under shear loading. Okay. It tilts like this. Now we know this one, and another example for I'm trying to give you different examples to understand where you can encounter these type of problems. Yes, here, let's say another example. If we have a timber connection, this is a timber member, this is wood, and a bracing comes here. These are the fibers on the wood, and if the load comes from here to this joint, what we are going to see, okay, this force has two components in two main directions. It comes here. The first one is the vertical component. You can calculate it depending on this angle, and one horizontal. Okay, the vertical one goes directly to this member, no problem, that's okay. But this, the horizontal one, comes here and push this portion, as you can see, this part. So this portion, there is an area here. Change. This area should transfer this shear stress due to this loading to the main body. So here we have an area. So again, there are shear stresses on the surface. And the other well-known example is bolted connections. we connect two plates with steel balls. For example, here we have one plate here, another plate is at the top. And here we have bolt. When we apply loading, this load comes here, and in between these two plates, there is only the connection area, is the circular area of the this bolt. There will be a shear stress on this area. If it works, yes, we can transfer it to the other plate. It works means if the calculated shear stress is less than the bolt's allowable shear stress, that's okay, it works. It transfers all the load to upper portion. If not, it doesn't work. We have to increase the number of the bolt, or we have to change, or we have to increase the size of the bolt to get higher area. Today, we are gonna learn how to calculate bolted connections. Okay, subject is really basic. There are a few things to keep in mind. If you be careful about that, you can solve all these type of problems. It's really easy, not so complicated. It's a straightforward method. So let's get started to bolted connections. Okay. So these are also important for your professional life. In professional life, you may encounter some steel-to-steel bolted connections. They might not be very complicated at that time. You should solve your problem. You should come up with a solution for that bolted connection. For basic connections, you can do your calculations and you can go ahead your works on site. Here, I will explain in two columns the problem. Let's start from the left-hand side. Here we have a top plate. Again, here a bottom plate. Okay, and we have here some balls. Bolt is a blown cıvata. Okay, so this is side view, and we apply load P, and let's have a look to plan view. This is the top plate, bottom plate is under this plate, that's why this is the rack line. Here we have a bolt, and the bolt is here, P is here. This is the first case. Okay. Let me draw the second case here. to talk about these cases at the same time. Here we have a plate again. Here we have the top plate. And the bottom plate. So in this connection, we have 3 plates. There is a mid plate and top and bottom plates. As you can see, here are the bolts. Okay. P is here, P over 2, and P over 2. Here P comes from this side. With using bolts, we transfer all half of the load to top plate and the other half goes to the bottom plate. As you can see, at the end, we have at the top and bottom plates, P over 2 load. Yes, and the plan view of this plate. A mid plate, which is black line. I have 1 bolt and bolt. Yes, this is the plan view of this connection. Now, let's get started from the first one. I will write the equation for each case, for the first and the second cases. Now, what I'm gonna say you, for the first case, if I'd like to transfer the load P to the other plate, how many shear phase I have? Basically, the question is this. As you can see, this is the plate 1, this is the 2. So there is only 1 shear surface in between 2 plates. Okay. 1. Let's have a look the same in the second case. So to transfer the loads, other plates, how many shear surface we have? We have here 1 and 2. These shear surface are where the plates touch to each other. Okay. So here in the first case, there are 2 plates touched to each other. That is the shear surface for my calculation. For the second one, there is a top plate and bottom plate. They touch the mid plate from top and the bottom. That means there are 2 touch surface. So these are the shear areas. We have 2 shear areas. Okay. We know this. Now we are gonna write the allowable shear capacity of 1 ball. Okay. PTM. PT. Okay. Now, if we have by the way, we know what we know. Okay, I'm gonna explain that later on. To one bolt shear capacity, what we do, the force is always area times stress. Okay, what we have for one bolt, we have a one bolt area, the sectional area, which is circular, times allowable shear stress of that bolt. Okay. At the end, it gives us one bolt shear capacity. Okay. If the by the way, let me draw a big sketch over here. Where here we have a bolt. Okay. Bolt has a diameter, right? So P, so it's P. This is the area of the bolt times so allowable. Okay, so allowable. This is what times. This is the total one bolt shear capacity. Remember, we talked about the shear surfaces. For example, we have one shear surface here. One shear surface. That means only one area works for shear. But here, one area means here we have a circular area, no? This area works for shear, for one bolt. But in the second example, we have shear surface here and one more here. For each bolt, two areas work for shear. Okay, so that's why only the one surface area works for shear, and this is the allowable stress times number of bolts times n. This is the number of bolts. Okay, number of bolts. This gives us times n. That's the total shear capacity of the bolts. Okay, total shear capacity of the bolts. Let's write the same equation for the second case. P, T. Okay, the bolt area is this. But for each bolt, since there are two shear surfaces, you can see the green areas here. Two bolt area works for shear. So if so, we have to take into account this number. We put it here, 2. So that means 2 area works for shear. Or we can write here number of shear plane. I don't want to memorize this number, or 2. If we increase the number of the shear planes, You have to be careful. You have to check the logic. Look at the number of touch surfaces. So each touch surface, in each touch surface, a bolt area works. As you can see, we have two bolt area which works for shear. That's why this is the one area, one surface area times 2, which represent the number of shear plane times so allowable. So allowable is coming from the question, or we know that, okay, because we are going to use a bolt, we know it's allowable stress, and then we use it, okay, times and number of bolts. This is the shear capacity of all, total shear capacity of all bolts on the connection. Okay. Now, there is one more effect on the bolted connection, which is bearing, ezilme, bearing effect. P sigma L. We are gonna calculate that. It's about the, let me draw a sketch for you again. If I cut the detail from top to bottom from here, what I'm gonna see for a bolt, I will see a rectangular bolt area, right? Rectangular bolt area. But if I look there in three-dimensional, if I look there isometric, let me draw it. Just it will like this. So the total area, section area of the bolt is here, a rectangle. Okay, this is the bolt section. So what we are going to do, we are going to calculate the this area times allowable stress. So how we can calculate this area? D, this is D. Here, thickness of the plate, T. But which T? If we have two different plates, so if their thicknesses are different, let me write it here. T1, T2. So let's write same thing for this one. T1, T2, T3. We have different thicknesses in this case. So at the end, we have to consider T. But which T? You know, if we have less area, remember, we have high stress because force over area, the logic comes from there. Sigma, force over area. So if the area goes down, sigma goes up. If we have less area, we are gonna have high stress value. That's why in this question, while we are to calculate this, the allowable bearing capacity, we will calculate this force. So that means stress times area. To calculate the area, we have to consider the minimum area. Okay, minimum area. So let's do it. D times T mean. What is this? The minimum of, change color, minimum of T1 and T2. Okay, this is the area, this area, times allowable stress. That's it. Sigma L allowable times N, number of volts. What we did again, let's take a look here. This is the volt sectional area. This is area. Area times stress. This gives us force for 1 volt times number of volts. If I have 10 volts, okay, times 10. I have 5 times 5, whatever. Here it's same for above. This is area. This is stress. This portion gives us the force times number of volts. Let's write the same equation for the second one. So D is D. The equation is same completely. D mean times sigma L allowable times N. Again, this is number of volts. Okay, the equation is same, but the question is here. What is T mean? In the first case, it was like minimum of T1 and T2 because there were 2 plates. Compare these to each other and select the minimum thickness. That's okay, it works. But here, what is the minimum T mean? So the logic is basic here. Let's take a look here. We have to consider the plate which works for same side. That means this plate works left side because the force takes it to the left. And these two works for the right side. Okay, right side. So the forces P over 2 takes them to the right-hand side. So we will combine the thicknesses in the same side. So at the end of the day, T mean is gonna be minimum for the left-hand side. What I have only T2, right? T2. Or for the right-hand side, the summation of or combined version of the right-hand side, T1 plus T3. Okay. This is the main logic you have to know here. If we have 3 plates, that means we have 2 shear planes. We consider 2 to take into account the number of shear planes. And also for the for the bearing stress, bearing, this is for shear, let me write bearing. This shear, this is bearing. Okay, this is bearing. Here, in this case, for bearing capacity of the bolts, D is D. Remember, from here, comes from this area. The question is T. What is T? Consider the same side, the thickness of the plates, which work for same side. For the mid portion, for the left-hand side, there is only one plate, which is T2 mid plate. For the right-hand side, top and bottom plates work for right. So take into account combination of these two, T1 plus T3. Okay. That's all for this one, actually. And these equations gives you the capacity of the bolts. So if you know that, okay, the critical question for you, you know, at the end, PT capacity, PG capacity. So shear capacity of the bolts, total bolts, and the bearing capacity of the bolts. Okay. If you don't consider the N at the end, this one, you only get the capacities for one bolt. If you multiply it, the total number of bolts, it gives you the total capacity of the bolts. Okay. Keep this in your mind. Now, the question is this. We have shear capacity and we have bearing capacity of the bolts, total or for one bolt, whatever. We have these two capacities. Okay. With what is the, so we have two capacities. At the end of the day, we have to convert it to one capacity. Okay, we have two capacities. Which is the exact capacity of the bolt connection? Okay, PT or PG. Okay, here is the critical question. The most of the students make some mistakes around here. Let me, okay, I guess you understand PT and PGL. Is there any questions so far or comments, anything else? If you have, I'm gonna ask this in midterm exam. Okay, this is basic. I will ask a question regarding this one. You have to know this. This is the basic. You have to catch this question. Okay, that's why if you have any trouble, please let me know to explain everything again and again, okay, for you. Any question? No, okay. Yes. Let's combine PT and PGL. Okay, we calculated two capacities, P2 and PGL. What was this? This is the shear capacity. This is the bearing capacity, right? Bearing capacity of bolts. So the total capacity of bolts, P bolt capacity, is minimum of these P2 and P of GL. Okay. The capacity, the total capacity, because we have two capacities, but which one I'm gonna consider in the questions, in the calculation of bolts, which one? we have to consider, we have to compare these two shear and bearing capacities, and the minimum one is the bolt capacity. Okay, minimum one is the bolt capacity. In exam, what I see is generally when you get these two capacities, you calculate these two, that's okay. But if you select the wrong one, the result is completely wrong. Generally, you select the maximum one. So if you select the maximum capacity, the maximum one in between these two shear or bearing capacities, you are going to get less bolt number. That means your connection will fail. That's why it's totally wrong. That's why you have to select the minimum. This portion is important. Okay. So for bolts, we have these two capacities. By the way, you know, in this bolt connection, we have bolts and steel plates, and also we have steel plates to check their capacities. I will do it in the example. Let me give you a few minutes to see. Do I have an example about this? Yes. Okay. Okay. The subject is this, actually. From now on, I'm gonna solve a few problems for you. And today, I'm gonna close the session earlier than we expect, because all the subject is this. There is nothing more about this one. Let me see example questions here. What I have. Yes. Okay. Before the question, I'd like to explain how to check. I was gonna explain this concept in the examples, but before that, I would like to explain it now. What is it? Okay, we just talked about fault connection. This is the plan view. Okay. This is the plan view. We apply force in this direction. So we have to consider, let me see, can we go back? There's no place to write. We need to check the plates, steel plates. Okay. Let's say if this is one shear, one shear plate. These are the bolts. Okay, and it may be like this. Okay. At the end of the day, we talked about the bolted connection, but steel plates also must be checked under this loading. So for steel plate, it's an axial force, because this is the area for steel. So this force is perpendicular to the steel area. So at the end of the day, this is an axial stress check for the steel member. For this one, what we do, we find the most critical location to check the steel. For example, you can check the steel on this section, or you can check it on the section where you have two bolt areas. So you should select the second one, where you have bolt holes. Okay, where you have bolt holes, because in the section 1.1 you have solid area, solid steel section. That's okay. But the most critical one, you have a total area in the section 1.1. But if you take a look at the section 2.2, by the way, let me draw these sections. Maybe that's better to understand. This is the section 1, the solid area. 1.1. And let me draw the section 2.2. 2. When you cut from the bolt holes, you are going to see two bolt holes on the section. That means these red areas are missing areas, and only black area works for the axial force. So that means the area is getting smaller. So at that portion, stress will increase, because the P, force is force. It's same force we have to transfer on the section. But if the area gets down, stress goes up. Remember, stress equals force over A. A goes down, stress goes up. The most critical, if we have higher stress, that's a problem for us. So that's why we always check the minimum area locations. Another question. Okay, by the way, let me mark it up. We check this section. Okay, another question. Let me draw it here. For example, you have a bolted connection again. Sometimes we can do these type of connections. So for this where do you check section? On 1, 1, on 2, 2, or on 3, 3. Okay, where do you check this section? Okay, when you compare these three areas, three sections, okay, at the end of the day, all of them have rectangular section. The second one is a solid section. There is no missing area. Okay, there is a solid section. It's the good section for it. We are looking for the most critical one. Okay, for the most critical one. That's why we have to find the minimum area on the section. So let's compare the section 1 and 3. On 1, we have only 1 bolt. On 3, we have 2 holes. So 2 bolt hole means we have 2 missing area, which will not work for our force. So the section 3 has critical area and has the minimum area. That's why we have to use the section 3.3 to make this check. Okay, this one. I guess you understand this logic to check this steel plate. One more thing. To make this calculation, we have to calculate the net area at the end of the day. As you can see in this example, we have to calculate the black area. We are gonna remove the red part from the total section area, and we are gonna get the black area, which works for the axial force. Here, what I'm gonna write here, there is something here. Let's say we have a bolt. Okay, the bolt hole is always greater than this bolt diameter 1 millimeter. Okay, let me write here. I'm trying to draw it well. It's not easy to draw good to the screen, but I'm trying my best. This is D, the bolt hole. Let me go here. The bolt is D. Okay, the bolt hole diameter is D plus 1 millimeter. Okay. Bolt diameter D. Bolt hole diameter D plus 1 millimeter. Okay. So we will, if we give you this bolt diameter, while you are calculating the net area, you will consider this one, D plus 1 millimeter. In the examples, you will see how to do it. Okay, how we give you the bolt diameters? Bolt diameters like this. For example, the bolts are named like M20. M means here metric. M20 is diameter of bolt, but in millimeter. Okay, this is the diameter of the bolt is D is here, 20 millimeter. The hole is 21 millimeter. Okay. Let's do another example. For example, if we have a bolt of M16, here the bolt is 16 millimeter, the hole is 16 plus 1 millimeter, so 17 millimeter. Okay, 17 millimeter. Okay, for the steel area to calculate, actually this part is regarding the previous week's subject, the axial force effect, normal force effect, but I'm trying to explain it again for you here. You get understand about the bolt diameter and hole diameter. So let's calculate the area for the one shear plane and two shear plane connections. Let me draw again this example here. This is the now remember what we have. T1, T2, here, T1, T2, and T3. Here the area, by the way, we have to know the plan view. I am not the number of bolts. Sections from here. Okay, remember, we have to know this B. Okay. Let's calculate the A net area for the first one. A net, the total area of the plate, critical plate for this connection, the first one. A net, total area, B times, again, T min, in between T1 and T2. This is the total sectional area. Or maybe you can do it, that's better. We are looking for the critical area. B is B total width of the section minus the bolt holes, right? We don't know how many, times T min. This is the total area times sigma allowable steel. By the way, we are talking about the area. We are talking about the area. This is the A net area. If we are talking about the P steel, capacity of the steel member, the A net times sigma allowable steel. This is a general equation. Actually, if we are doing the one shear plane connection, case one, we compare two sections, two thicknesses, T1 and T2. That's okay. Select the minimum one. And if we are doing the two shear plane connection, second one, Tmin is gonna be as the bearing stress T2 or T1 plus T3. Select the minimum one for this part. You are gonna do this Tmin decision at the bearing capacity of the bolt, and then put it here directly. It gives you the area. The net area times the still allowable stress gives you the still capacity. At the end of the day, you have the shear capacity of bolt, bearing capacity of bolt, axial capacity of steel. For this connection, minimum of these three capacities is the total capacity of that connection. If we are talking about the connection, we have to consider bolt capacities. We have two, shear and bearing, and also shear steel capacity. So minimum of these three gives you the capacity of that connection, not only the bolt. We are talking about the connections capacity. This connection, how much load this connection carry. Okay, do these calculations, select the minimum of that. That's it. Okay, let's have a break, and then I'm gonna solve you a few questions. They're so easy. We're gonna use this method, straightforward method, so we can close the session today. Okay, see you guys. Our break is half an hour. We're gonna be here at 10:45. See you. Okay, we're gonna start to solve examples regarding the shear effects, especially about the bolt connections. First one. Section. Inside. There's a word large plane. Here. Here. Yeah. Okay. This is the section view. Key here is 25. By this is 8 millimeter, and thickness of this is 12 millimeter. So all the other unknowns, allowable stresses for bolt, so allowable. And force T, sigma allowable is okay. Now, here, determine the bolt quiet. Number of bolts to transfer load P safely. Okay. This question asked to us. By the way, the diameter of the bolt is 20. Okay. In this question, you can see there are two plates in both sides, this one and this one, and there's a big plate inside at the mid portion. The force P is 25 tons, and the thickness of the plates are given on the sketch, and the bolt diameter is also given on the sketch. Question asked to us, how many bolts do we need to transfer this 25 tons? Okay, here we don't know the number of bolts. Okay, I've drawn the bolts like this. We don't know how many. Question is this: how many bolts do we need to do it? We don't know the one capacity of the one bolt. We have to calculate it beforehand. What we should do when we have a look at this connection, we have to decide the shear plane number. As you can see, we have 3 plates, and the section we have 1 shear plane here and 2 shear plane here. Okay, number of shear plane 2. Okay, we decide this one. Okay, let's get started to calculate P for one bolt. Remember, we are going to calculate the area of the bolt. Okay, sectional area. P is M20. Remember, M20 here. D is 20 millimeter equals 2 centimeter, right? I use this 2 centimeter because I have to make a unit conversion since all the given allowable stresses are in kilogram centimeter, as you can see in centimeter. There in centimeter, I convert the 20 millimeter to 2 centimeter here. This is the area for the one M20 ball. Okay, times, but we have two shear plane. That's why two section of this ball works for shear. I'm gonna put here a 2. This gives me total area of the ball times allowable stress. I'm dealing with the shear stress. That's why I'm gonna put the shear stress over here. Okay. This gives me the shear capacity of one bolt. Let me write here. Okay. This is the shear capacity. Let's write the bearing capacity. D. We know D. D is the diameter of the bolt in centimeter cube. T mean. Remember, what was it? We are gonna write it here. Let's calculate it. These two, the goes right hand side. If 12 goes left, so T mean is 12, 8 plus 8. So at the end of the day, T mean is 12 millimeter. I'm gonna put it here as in centimeter, 1.2 centimeter. Right. Yes. Times D times T mean times sigma L allowable. Look here. It's 2,400 kilograms. If we make this calculation, its capacity is this. Now, the question asks only the number of balls. Okay, here. So, since the question is number of balls, we have to decide the bolt capacity. P bolt. The minimum of P tau and P sigma L. So we have two numbers. Which one is the capacity? That's the minimum one is here. This. So number of balls. The total force is 25 tons, 25,000 kilograms, and okay, what we get from here, 4.34. Here we have to round this number up. Okay, as you can see, the number of bolts should be or must be higher than, greater than 4, as you can see, and round up number, we need 5 M20 bolts. Okay. This question gives us the how to calculate the number of bolts. Okay. Okay. Any other question? Let me see. Yes. Then question. Okay. Let's solve another one. I'm going to change the question a little bit. Here, let me see. So I'm trying to make the question is that I can find already question from here. Because let's count the output at the end. Let me check question. Let's find this. So I'm going to clear it completely. I'm going to write the question. Start to build a new question here. Okay. Here. We have both connection again. The section we have 1, 2, 3 volts in the section. Differences here. Then we go to plan view. Okay. Width of the plate is 100 millimeter. And what we have 6 and 20 bolts. The 4 bolts to allowable this for steel. Question is determine the maximum load capacity of steel plated connection. Okay, this one. Now, what we are gonna do here, we will have three cases. The question asks about total capacity of this connection. What we have for bolts, we have two cases. One is shear, the other one is bearing. And also for steel plate, we have axial stress check. Okay, but at the beginning, what we should do, we should decide the number of shear planes. We have 3 plates. That means we have 2 touch surface. One shear plane is this, other one is this. That means for each bolt, 2 area will work for both. So number of shear planes, 2. Okay, number of shear planes, 2. Bolt. What is the bolt diameter? Bolt diameter. We have 6m20. M20 means we have a diameter of 20 millimeter and 2 centimeters. Okay. What is the bolt hole diameter? +20 1 millimeter. So 21 millimeter equals 2.1 centimeter. Okay. At the beginning, we can decide all these numbers. Then we can use them. Okay, let's write P2. Okay, let's write the area. P times D. D is 2 times number of shear planes. 2. This is the total area for one bolt. For one bolt times allowable stress. The allowable stress is here for shear 1.12 ton per square meter for some centimeter square. Now we have capacity of one bolt. But what's the question? Total capacity of this. We can add 6 here. This is the number of bolts. Okay. So here we're going to see the result of this. P sigma L. D is the diameter of the ball. Diameter of the balls. 2 times T mean. What is the T mean? T mean here is we have one side 8 plus 8, other side 20. Minimum of 8 plus 8 or 20. So Tmin is here 16 millimeter. Okay. 1.6 centimeter. Okay, this is the Tmin. D times Tmin times allowable stress, which is 2.4 times number of bolts equals, the result here is yes. Now we have the bolt capacities for shear and bearing stress. But what we are talking about, we are talking about here this steel connection capacity. So here we have to consider the area, the capacity of the steel plate. So let's do it. Let's see. P steel. So area, but we're gonna calculate this area on the most critical section here. Okay, where we have two bolts. Okay. You know the bolt hole diameter. So total width of the plate is 20 centimeters, right? Minus how many bolt holes we have in the section? 2. Minus 2 times here, the bolt hole diameter, 2.1 times Tmin. Tmin, what was Tmin? 1.6 width times thickness times allowable stress, which is 1.4 ton here, equals what? Okay, this is the steel plate capacity. So at the end of the day, what is the P connection capacity? Okay, we have these three numbers. We have to decide the capacity. For the capacity, we have three capacities, and the minimum of these three capacity gives us the total connection capacity. Okay, the connection capacity here. Why? Basically, if we select the capacity as the maximum, for example, if we select the capacity like this one, 46. Okay, the load on the connection increase step by step. When the load meets the 35, steel plate will fail. Okay, I know my bolt will fail on higher values, higher loads, but before then, my steel plate will fail. So that's why we can't select the maximum capacity for the total capacity. We have to always look for the minimum one in these capacities. Okay. This is the total capacity of the connection. And another question. Let me see. Check. Scientific type of question. Question is good. I don't have the solution, but we can do it. Yes. I have a bolted connection again. This is the side view here and here. P 9 times. So what we have one. This here is and plan. P. We have 1, 2, 3, 4. There are 4 M16 bolts on this connection. Okay. So width of the plate 150 millimeter. Okay. Question here is, by the way, for bolts again. For a low bolt, 1.4. My L low bolt is 2. And for steel, sigma and low bolt. Okay. Here the question is perform all required checks for given voltage connection and determine if it is safe or not. Okay, we have this connection. So it transfers 9 tons and all the plate thicknesses, widths, and all other dimensions are given on the sketch. We are going to decide if this connection safe or not. Okay, safe or not. So to do this, we have to calculate the total capacity of this connection and compare with the load P. Okay, let's do it. By the way, before to start this calculation, let's find the number of shear planes. There is only one touch surface, so number of shear plane 1. Okay, there's only one shear plane. So the bolt hole here, bolt diameter, by the way, the bolt diameter is 16 millimeter and 1.6 centimeter, and bolt hole diameter is 16 millimeter. Don't forget this one. The bolt hole diameter must be calculated first in millimeter, then you should convert it to centimeter. Plus 1 millimeter. It's 1.7 centimeter. Okay, we know all these numbers. Let's do the calculation. P shear capacity. D is P times D 1.6 over 4. This is the area times number of shear plane is 1. You know, we don't need to write it here, but I write it here to keep in mind. There is a number of shear plane here times allowable stress 1.4. Okay. I'm going to calculate the results. First, let me write all the equations, then calculate the results. I don't have the solutions. Sigma L. It's D. Remember, D times T min. D is the diameter of bolt. 1.6 times T min. T min is what? We have 2 plates here. T min is easy here. Compare 8 and 12. The 8 is the minimum one. 8 T times T min in centimeters times allowable stress. By the way, we can add now the number of bolts here. You know, number of bolts is 4 times 4. We can get the total capacity with this calculation. Now that's okay. This is D, T min, sigma L, allowable, and this portion is number of bolts. Now, here, number of shear plane. These capacities are for the bolts. Now we're gonna do it for the steel. P steel. Okay. The critical section here is where the maximum bolt number are placed on the section. This one or this one, whatever. It has a rectangular section. There are 2 bolt areas which are missing, and the shaded area will be calculated. Now, total width is 15 centimeters minus 2 bolt holes, 2 times bolt hole, 1.7. This is the width times T min. T min is 0.8 times area. This gives us the area. This is the area times allowable stress for steel 1.4 equals 1. Let me calculate this number. Let's calculate the first one. P times 1.2 times 1.4 over equals 11 point. This is the capacity for shear 1.608 times 4. Yes, correct. Last one for steel minus almost 13 tons. So here P connection capacity is, when we compare all these numbers, minimum of all these three capacities gives us the connection capacity. This is the connection capacity. Okay, is it safe or not? Let's compare with the given loads on sketch. Given load is 9 tons. So it's less than the capacity. So 9 tons less than the capacity. So it's safe. Okay. Okay, any question so far regarding this example? Any comments? Okay, if you don't have any question, that's all from my side today. Thank you for joining class today. I hope to see you again next week. Now we completed the shear force effect. Next week we are gonna. By the way, next week we are gonna do application, and the week after, next, we have the Children's Day. It's bank holiday. We are not gonna be here. So the week after the Children's Day, we are gonna have our midterm exam. So that means this is the last subject before the midterm exam. Next week is the last class day before the midterm exam. I recommend you to join class next week. Okay, we are gonna solve only questions regarding all these subjects that we talked so far. And then you're gonna study for midterm exam. We will see each other in the midterm exam day on actually 30th of April, I guess. The last day of April, we're gonna see each other in midterm exam. Okay, take care of yourself. Have a good weekend. Bye-bye. By the way.